Hello viewers, welcome to All Force e-learning program. I am DNR, physics lecturer. Now this is the physics session number 7. It is the 7th session. The physics we were dealing with vectors. So we have dealt with the various things. Let's have a recall of what we have done so till date. Later on we will move on with this. So I was telling you, physics is a subject of measurement, right? Whenever you measure something, you get a physical quantity. All physical quantities are classified into two: scalars, vectors. So scalars, I was telling you, the physical quantities which possess only magnitude but have no significant direction. Even if they possess direction, the direction has got no importance. They do not obey the laws of vectors. So they are scalar quantities. There are many scalars: fundamental quantities, physical constants, many of the thermal quantities, wave properties, etc., etc. Now coming to vectors. Vectors are physical quantities which possess both magnitude, significant direction, and they obey the laws of vector addition. It is not just mere possessing magnitude and direction does not mean that they are vectors. They have to obey the laws of vector addition. Then only they are said to be vectors, right? So vectors have both magnitude and direction. They are represented by a line segment, a straight line. The length of the line segment gives you the magnitude and the arrowhead gives the direction. They are represented by three methods: pictorial way, mathematical way, and the polar method of representing the vectors there. Okay. So that way these vectors are represented in three forms. Later we have dealt with the different types of vectors. I was telling you first the coplanar vectors or collinear vectors, co-initial vectors, co-terminal, coplanar, collinear, then parallel vectors, anti-parallel, like and unlike, equal, negative vector, unit vector, zero null vector, and unit vector. Later on, then we have dealt with the unit vector, Cartesian 3D system of representing position vector, finding out the position vector of any point in the Cartesian plane, right? So Cartesian 3D frame, you can find the position of a point there. Is it? Suppose if x, y, z, this is the Cartesian 3D system, right? There is a point P, x comma y comma z, suppose. Then the vector which represents the position of the point P, OP. So OP bar is the position vector of point P, and it is represented as x I cap plus y j cap and z k cap. This is the position vector. If the coordinates are x comma y comma z, then the position vector is xi, yj, zk. Next, the magnitude of the vector OP bar. It is under root of x square plus y square plus z square. The magnitude, right? The square of the sum of the square of the coefficients. It is root square, sum of the squares under root, whole root. So it is the magnitude there. Then the components, x component is x, y component, z component, the respective coefficients of I, j, k. Well, I cap, j cap, k cap are the unit vectors along positive x direction, positive y direction, and positive z direction. Next, the components are x, y, z. Then the angles made by the vector with x axis, y axis, and z axis. Angle with x axis alpha, y axis is beta, z axis is gamma. So therefore cos alpha, cos of the angle made by the vector with x axis, it is x by under root, the I coefficient x by root of x square plus y square plus z square. Similarly cos beta, it is y by under root of x square plus y square plus z square. And the third one is cos gamma, it is z by under root of x square plus y square plus z square. So this way you find out the direction of the vector by cosine angles. They are called directional cosines of the vector, right? So the coordinates, position vector, magnitude, components, directional cosines. This way you find out the position vector of a point in a 3D plane like this. Okay. Then we were talking about what happens when a real number is multiplied to a vector. So the topic what we have left in the last session was multiplication of a real number to a vector. So what happens when I multiply multiplication of a real number to a vector? Now what happens when I multiply a real number to a vector? Let's understand, let's analyze this. Consider a vector a bar. Let's suppose there is a vector a bar, right? So it is represented by a line segment, let's say from O to P. OP bar is the line segment. So length of OP bar gives you the magnitude. So I was telling you magnitude is the absolute value of the vector. The absolute value of the vector is termed as magnitude. It is actually termed as modulus of the vector, right? So the magnitude of A, mod A is the length of the line segment O to P, magnitude. This is the magnitude of the vector. Now what happens when I multiply a real number to this vector? Let's say suppose if this is vector A bar, I have multiplied a real number, let's say K. Some K is multiplied to the vector K A bar. So whenever a real number is multiplied to a vector, this will yield another vector, some A dash bar. A dash bar, right? It gives it another vector A dash bar, right? So whenever a vector is multiplied to with a real number, it gives another vector A dash bar, such that the magnitude of A dash, so magnitude of A dash bar is K times the magnitude of vector A. So the magnitude will be K times this. If K is greater than 1, the magnitude is more. If K is less than 1, magnitude is less, right? So the magnitude of the resultant vector will be K times the magnitude of this. And the direction, the magnitude is K times. Then how about the direction? So if K is greater than 1, so this will be A dash. And the direction will be same as this. It is same as this of the first vector A bar. So the direction of A dash and direction of A bar is same. So direction of A dash bar is same as it is same as A bar, the direction of A bar. A dash bar, direction of A dash is same as that of A bar. The direction is same. Now A bar and A dash bar will behave as like vectors. They are in the same direction. Both are same magnitude, same unit. They correspond to same unit because I have just multiplied it with a real number. So magnitude is changed. Unit remains same, direction remains same. They are like vectors. Well, suppose if K is positive, they are like vectors, right? So we shall analyze. So whenever a vector is multiplied with a real number K, then it will yield a resultant vector A dash bar, which is again a vector. Then in this one, let us suppose if K is greater than 1, bigger value, greater than 1, then implies the magnitude of A dash bar will be greater than magnitude of A bar. If K is greater than 1, this will be more than this, obvious, K times more. So magnitude of A bar will A dash will be more than A bar. So A bar is up to OP. Now A dash will be bigger than this. But they are in same direction and in same direction. Same direction. Now if K is less than 1 but greater than 0, like K 0 less than K less than 1, then the magnitude of A dash bar will be less than A bar. So this time if K less than 1, so if it is A bar, so A dash bar will be a bit less. If it is half, 0.5, half, right? So less, but the direction is same because it is greater than 0, positive, and in the same direction. Acha, next third, if K is greater than 0, implies, so K greater than 0 in the sense it is positive. This is also positive. So A dash will have the same direction as that of A bar. So A dash will have a magnitude K times A bar, and it has same direction as A bar. Now A dash and A bar both they are like vectors. They will behave as like vectors. Now if K less than 0, what does it imply? k less than 0 in the sense it is k less than 0, negative value, minus. So I am multiplying a minus value to a bar. When I multiply minus to a bar, then a dash bar will become, a dash bar is, it's a negative value. So it's minus the magnitude of k into a bar. So now a dash bar, of course the magnitude is k times a bar, magnitude is k, but it is in opposite direction, but in opposite direction to a bar. It is in opposite direction to a bar. So therefore a dash bar and a bar will be now unlike vectors, or unlike vectors now. They are unlike vectors. Let me represent them by picture form. In the first case, first case k greater than 1. Suppose this is a bar, imagine a bar. K greater than 1, then the magnitude of a will be k times a bar, which is more. So now the vector a dash bar will be like this. The magnitude is more, but in the same direction. First diagram. In the second diagram, this one, here what happens? So this is a bar. Then if it is k less than 1, then a dash bar will be smaller when compared to a bar. But same direction. It is greater than, k greater than 0, less than 1. So magnitude is less, but the direction is same. Third, if k greater than 0, positive, a bar and a dash bar will be in same direction. Right? Magnitudes are different, like this. But in the fourth case, if a bar is like this, then a dash bar will be in the opposite direction. A dash bar will be in the opposite direction. They are unlike vectors. Here they are like vectors. Here they are unlike vectors. In these three cases they are like vectors. But in this one they are unlike vectors. They become opposite. Minus. Example. Suppose if I give you an example. Force experienced by a negative charge, electron. Suppose if there is an electric field E, then the force experienced by an electron E minus, the direction becomes opposite. It is opposite to direction of this. Right? If I multiply a negative value, then the direction, these two are in opposite direction. Force will be opposite to the electric field. Minus. So that way it is. So whenever a real number is multiplied to a vector, the vector changes either in magnitude or in direction. Right? Magnitude changes by k times. Direction, if k is greater than 0, direction will not change. For k less than 0, direction becomes opposite. Right? So whenever a vector is multiplied by a real number, right, then there is change in the magnitude of the vector. For all k greater than 0, positive, only magnitude changes. If k negative, direction gets reversed. Direction becomes minus. Suppose, let us take a simple example based on this. You see, I was telling you, right, this is x-axis, this is y-axis, and this is z-axis. You know, unit vector along x-axis is I cap, 1 unit. So if I multiply 2 to I cap, then in it is 2 units. So the vector is 2 units like this. If I multiply 5 to I cap, then 1, 2, 3, 4, 5, the 5 units of this vector it is like this. Similarly, 1 unit in j is j cap. Suppose if I multiply some 4j, 4 I multiply 1, 2, 3, 4, so it is 4j like this. So magnitude increases those billion number of times. The direction remains same. Right? Similarly, k, if it is k, 1 unit is k. If I write 7k, 1, 2, 3, 4, 5, 6, 7, so it's 7k like this. So whenever you multiply a real number, the direction remains same, the magnitude will change for all k greater than 0. Suppose if I multiply minus number, let's see, if I cap, I multiply minus 3. So then the direction is reversed. So I is positive x-axis, now it will be negative x-axis. Minus 1, 2, 3, so minus 3 units. So this is minus 3 I cap. Right? This is 1, 2, 3, 4 by 5 I cap. This is 1, 2, 3, 4, 4 j cap. This is 7 k cap. This is 3 units minus 3 I have multiplied. Suppose if I multiply minus 4 j cap, I multiply minus 4. J is this side upward, then downward. 1, 2, 3, 4. So it's downward direction minus 4j cap. Like this. So this way, the vector, whenever a real number is multiplied, if it is a positive number, positive real number, direction remains same, only magnitude changes. Negative real number, then the direction gets reversed like this, right? Now, in one of the entrance examination, there was a simple question asked like this. There are two vectors, A bar and B bar. The angle between A bar and B bar is something like 60 degrees. Then he asked you, what is the angle between 2A bar and minus 3B bar? Now this was the question. A very simple question. The angle between A bar and B bar is 60 degrees. Then what is the angle between 2A bar and minus 3B bar? This was the question. Let us try to simply picturize the question like this. The angle between A bar and B bar is 60 degrees. Let's suppose A is in this direction. This is A bar. Now B bar is in this direction. The angle between them is 60 degrees. So this is A bar and this is B bar. Right? The angle between them is 60. Now he said, what is the angle between 2A and minus 3B? Now what is 2A? If A is this vector, 2A, the magnitude is twice that of it. So this vector represents 2A. Then minus 3B bar. B bar is in this direction. Now minus in the sense the direction is reversed. So it will be in the opposite direction 3 times. B, B and B like this. So this is minus 3B bar. Now the angle between these both. You know, whenever you are asked to take the angle, I was telling you, to measure the angle between the two vectors, they must be co-initial vectors. They must start from the same point. Their initial point should be same. So co-initial. So now this is 2A bar and this is minus 3 bar. They are starting from this point. The angle between them is this. But you know, this total angle is 180. Out of this is 60. So this is 180 degrees minus 60. It's 120 degrees. 2 pi by 3. This was the answer. So the angle between, the first two he has given, right? Then he has changed the sign. Then the angle changes in this manner. So this way, you can find the angle after multiplying the real number. You can find the angle like this. Now let us understand what happens when I multiply a scalar to a vector. Now we have dealt with the, we have dealt with multiplication of a real number. A mere real number is multiplied to a vector quantity. Then we have studied what happens. But suppose if I multiply multiplication of a scalar to a vector. If I multiply a scalar to a vector, now what is going to happen? What happens when such multiplication takes place? You know, multiplication of scalar and vector is a valid operation. You can multiply. You cannot add a scalar to a vector. This is not valid. Even the subtraction of scalar and vector is also not a valid operation. You cannot perform this. But you can multiply scalar to a vector, and you can even divide a vector by a scalar. Sorry, you can divide a vector by a scalar. Vector by scalar is possible. Multiplication is also possible. Now let's see what happens when I multiply scalar to a vector. Let's suppose there is a vector A bar. So there is a vector A bar. Now I am multiplying a scalar S to it. So I am multiplying scalar S to it. Then this will change to another vector, let us say some B bar. It changes to another vector B bar, where B is SA, such that now this scalar, if it has a unit, if it is having a unit, then this unit into this unit, the unit of B has changed. The unit also will change. So there is, whenever a scalar is multiplied to a vector, then magnitude changes. The unit of the quantity also changes. The nature of the quantity has changed. For example, suppose if this is, let's suppose this is some acceleration. Right? So this is acceleration A bar. And I am multiplying a scalar mass. mass into acceleration, this gives you force. Right? So it is acceleration meter per second square into kg. Now it is force, it is in newtons. The unit has changed. Unit changes, the physical quantity itself will change. The physical quantity itself changes, unit has changed, right? And the magnitude also changes. Now if the scalar is a positive scalar, then the direction of both direction of B and A remains same. So mass is always positive, mass cannot be negative. So if this is mass, then these both will have same direction. That is the reason why force is always, acceleration and force both are in same direction. Acceleration takes place in the direction of the force, resultant force, net force, right? So therefore, whenever a scalar is multiplied to a vector, then it yields another vector with a different magnitude, different unit, the quantity itself will change, a different quantity is produced, but the direction will be same, but same direction if the scalar is positive, and opposite direction if the scalar is negative. Scalar can be negative also, negative charge, electron, minus E. If I multiply negative charge, minus, then it changes, it will change. So therefore, whenever a vector is multiplied with a scalar, then it will yield another vector. It yields another vector of different magnitude. Magnitude changes, its unit changes, there is change in unit, the quantity has changed, there is new quantity that has arisen, and for S all, if the S is a positive value, then the direction remains same. If S is negative value, the direction is reversed. So whenever a scalar is multiplied to a vector, you get another vector. But this new vector has different magnitude, different unit, the quantity, you get a different physical quantity. Direction, if the scalar is positive, direction is same. Scalar negative, direction opposite. So that way, whenever a scalar is multiplied to a vector, it yields. Let me give you some examples. Example, displacement is equal to velocity into time. Velocity is a vector, time is a scalar, velocity into time gives you displacement. Momentum is equal to mass into velocity, velocity vector into mass scalar gives you momentum. Force F is equal to mass into acceleration. Impulse is equal to force into time. Right? So this way, these are scalar, time is a scalar, mass, time are scalars. Multiplied with vectors give you another physical quantity. You see the physical quantity itself has changed. The quantity changes. Different, you will get a different physical quantity. Well, direction again, if the scalar is positive scalar, then you get the same direction. Direction is same. And time is always positive, time cannot be negative. Negative time is past, you cannot, it is abstract, you cannot define. So therefore, this is positive. Mass is always positive. So always they have same direction. Sometimes if the scalar you have multiplied is negative, minus, then like force acting on an electron. So electron charge minus into electric field. Minus, the direction has reversed. The direction itself will get reversed. Well, quantity has changed, unit has changed, but now the direction is also changed. So in this case, all the things change. Magnitude changes, unit changes, the quantity changes, direction is reversed. Right? So these things are possible. These things are possible. So whenever a vector is multiplied to a scalar, it will yield another vector. You get another vector such that that vector has different unit, different physical quantity, magnitude is changed, direction, if the scalar quantity is negative, direction, scalar can be negative also, right? Negative scalar, charge, negative, potential, negative, right? There is every possibility that the scalar can be negative, okay? So this way, multiplication of a scalar with vector. Is it? Now next let us start with another topic called resolution of vector. Resolution of vector. You know, this is an important property of a vector. You know the difference? Scalar cannot be split into components. You know, vector, vector can be split into components. You can split this into any number of components. How many number of components can a vector be split? Infinite number of components you can split. You can split into infinite. You can have infinite components to a vector. You can have the component. Component is the shadow. I was telling you that day. Suppose if I take a vector like this. You want the component of this vector in this plane on the ground. Let's suppose this is ground. Right? There is a vector this way. What is the component along this horizontal surface? Imagine a light source here. Then for this, what shadow? Drop a perpendicular. The shadow on this plane represents the component. I can even have its component not in this direction. Suppose there is an inclined plane like this. There is an inclined plane existing. There is an inclined plane. Now the component on this, drop a perpendicular onto this. Now this will be a component. This way I can have its component in any plane. I will have infinite components. So a vector can be split into infinite components. Now suppose if I split it into two rectangular components. So let me imagine x and y axis. There is a vector a bar. Now I want the components of this vector along x and y axis. This is horizontal, let us say, and this is vertical. Usually in physics, usually we are in need of horizontal and vertical components. Usually, not always. You can even have different components also. But usually we come across in our environment, we need to have our known directions are horizontal directions, vertical direction. So we need to split the vectors into horizontal and vertical components. Usually. Then, now how can you do so? Then, so if this is, let's suppose horizontal direction, imagine x-axis. This is vertical direction, let's say y-axis. I want the component of this vector along horizontal and vertical direction. Now, so imagine a source of light, then the perpendicular. So the shadow of this vector on the horizontal plane. Now this is its horizontal component. Let's say this is OM. Similarly, imagining a source here, drop a perpendicular onto this. When you drop a perpendicular onto y-axis, this is the vertical component. ON. O is the origin. So OP is the vector. OP is the vector A bar. Its horizontal component is OM. Its vertical component is OM. Then the magnitude of the vector is mod A. So therefore OP bar is A bar. Magnitude of OP bar is mod A bar. And the angle made by this with the reference line. My reference line is the horizontal like this. Then the reference line is horizontal theta. Then so therefore theta with the horizontal. If such is the case, then how do you find its components? You can find the components of a vector. You can split it in any direction. You can split it in horizontal vertical direction or along an inclined plane, or you can split into vertical or along a string you can split. There are many such cases. We come across many such instances in our further study. So first simple case I am taking, if I have to split a vector into horizontal vertical components, then how I can do so? So this is the method. Component is just referred as, you can just understand it as, it is the shadow of the vector. If I take a vector, imagine a bulb, the shadow, what shadow it falls on it, that is the component of a vector, right? So another thing, component of a vector is always a scalar. It is just a mere number, a positive mere number, just value, right? Its component is always a value there, mere number there, okay? So therefore, when I split this into components, so consider this right angle triangle. I have dropped a perpendicular like this. When I drop a perpendicular, this is right angle triangle. OPM is a right angled triangle. OPM is a right angled triangle. Then in this right angle triangle, suppose if I take cos theta. Let me imagine cos theta. If I consider cos theta there, cos theta is adjacent side by hypotenuse. Adjacent side by hypotenuse. Then cos theta adjacent, it is OM by the hypotenuse is OP. So in this triangle, in this right angle triangle, take cos theta. Cos theta is adjacent by hypotenuse. So it is adjacent OM by hypotenuse is OP. Then I cross multiply. So what is OM? OM is OP cos theta. OP is the magnitude of the vector, magnitude. So magnitude of the vector A bar mod A, let us say it is small a. Let's say it's small a. So OM, I can write it as small a cos theta. So the horizontal component of this vector OP bar along the horizontal this direction, it is a cos theta. The horizontal component is a cos theta. Similarly, the vertical component OM. You know, I was telling you on that day, whenever you consider vector, when you shift the vector parallel to itself, there is no change, right? So therefore, this is OP bar. The horizontal component is OM, vertical component is ON. If this is ON and this is also ON, because both are equal and parallel. So therefore, from this right angle triangle, consider sin theta. Sin theta is opposite by hypotenuse. So opposite is MP by OP. MP by OP it is, right? So cross multiply. So MP is equal to OP sin theta. MP is OP sin theta. So therefore MP is equal to OP. OP is A. This is A sin theta. MP is OP sin theta or A sin theta. So the horizontal components of vector OP bar, the components of vector OP bar are, first horizontal component is OM and the vertical component is MP. MP is nothing but ON. So therefore this is nothing but ON. So this is ON, or ON is equal to A sin theta. So OM is the horizontal component and ON is the vertical component. Right? So where the components of vector OP bar are OM and ON, where OM is A cos theta, the magnitude, so OM is mod A cos theta and ON is mod A sin theta. So this way you can find the components of the vector there, right? And you know, when you combine these two components OM and PN like this, right, when you join these two, the resultant of these two is this. Now from this right angle triangle you see OP square is equal to OM square plus PM square or MP square. So OP square is equal to OM square plus PM is nothing but ON, so it's ON square, right? So OP square is, what is OM? A cos theta whole square. What is ON? ON is A sin theta, so A sin theta whole square. Now this plus this, if I take A square cos square theta, A square sin square theta, take A square common, sin square theta plus cos square theta. You know, according to trigonometry, sin square theta plus cos square theta is 1. So you will get it as A square. So OP square is A square, OP is nothing but A, magnitude of this thing. So again the resultant of these two components again will give you the vector A. The resultant of these two always gives the vector A. So the components of the vector OP bar and OM and ON such that the resultant of these both is again the vector. So that way you can find the rectangular components of a vector, perpendicular components of a vector in a plane. You can split this in any two direction, right? In any way you can split. So resolve is split, separate, you split, separate. So resolving the vector into components. You know, in this thing, what we do is consider a vector A bar, OP bar, it's A bar, right? The length of the segment is magnitude, that is mod A bar. Let the angle made be theta with horizontal. I want to find its horizontal vertical component there, right? So with the horizontal, the reference line is horizontal, I am taking an angle theta. So the horizontal component is OM and the vertical component is ON. Vertical component is ON, horizontal is OM. Then cos theta adjacent by hypotenuse, OM by OP. But OP is nothing but OP cross multiply. So OM is OP cos theta. OP is A, so it is A cos theta. Similarly, suppose if I take sin theta, MP by OP. So MP is OP sin theta. OP is again A, so that is A sin theta. So whenever you split a vector into two perpendicular components, the horizontal component is A cos theta, vertical is A sin theta. You know this horizontal component, this is right, Actually, this is the component adjacent this to this angle. The adjacent component, the component adjacent to the angle, adjacent component is always cos component, and the perpendicular component is always sine component. Sine. Had this angle, if instead here, if the angle been theta here, then to this angle, this is the adjacent component, the adjacent component, the angle theta. So this is the adjacent component. Then this will be a cos theta, and this will be the perpendicular component a sin theta. So we have considered theta. This is theta, for which I get this as the horizontal component. Is it? So horizontal is a cos theta, vertical is a sin theta. So that way you resolve or split a vector into two perpendicular components. So remember, always whenever a vector a bar is split into two components, this two components, there are two components, and there is a vector a bar like this. So a vector is split into two components like this. Its horizontal and vertical components. So for this vector, the shadow, its shadow on the x-axis, right? This will be horizontal and this will be vertical component. So that way you find out the resultant, the vector of the components of two vectors like this. Okay, so this way we'll do it. Yes. So whenever a vector is split, the components a cos theta, a sin theta like this. Let's take an example. We'll take an example based on this, how it will be helpful for us in our further study, in our future chapters. Suppose, imagine a string like this, a body is suspended by a string like this to a rigid support. There is a ceiling, rigid ceiling like this. To the rigid support, a body suspended by a string like this. Is it? If I lift this through a small angle theta to this position, in this position here, right, then in that position there, suppose at this position, if I take the components, tension in the string, if I consider the tension in the string like this, T, suppose T, the tension in the string, the force exerted, the force that is being pulling the string in all directions like this, string, tension, let's suppose this angle is theta. Let me imagine this as the origin, and this is the horizontal and this is the vertical. This is the horizontal direction and this is the vertical direction. So first of all, whenever you want to split a vector into components, resolve into factors, first you should imagine the axis, the direction, the components, the rectangular directions along which you want to split. In what perpendicular components you want to split, first you have to imagine them. So this is the point where the force is acting. It is localized at this point here. And now I am imagining this as horizontal direction, this is vertical direction. The string, actually, string is pulling the body in this direction. The tension in the string is T here, T, tension. You know, this is vertical line, this is also vertical line, both are parallel, and this is the transversal. You know, if this is theta, this is also theta. Now I want to have the components of tension T along horizontal and vertical directions. Along horizontal direction, vertical direction. Now this is the vertical component there. Let us say Ty, Ty. And this is the horizontal component like this. This is Tx. Well, the vector is in this direction. It is in this direction. It splits into these components. You know, suppose if the vector is in the first quadrant, let's say first quadrant, vector A bar in the first quadrant, then the components will be along Ax and Ay. So then vector A bar can be represented as, then I can write A bar as Ax along x-axis I cap, Ay along y-axis j cap. Instead of that, suppose there is another vector in this direction, in the second quadrant, B. Let us say the vector is B. Now this is split into components. This is horizontal Bx, vertical is By. Then the vector B bar is represented as, now Bx is in this direction, negative. So it is minus Bx I cap plus By j cap. Similarly, suppose if there is a third vector in the third quadrant, let's say like this. This is first quadrant, both positive. Second quadrant, x negative, y positive. Suppose if it is in the third quadrant like this, C bar, then this is Cx and this is Cy. The components will be like this. You see, when you split a vector, this is a vector, the components are in this direction, x and y. If you split this vector, it is x and y. Split this vector like this, it comes out to be like this. Then the vector c bar, then c bar is minus cx I cap minus cy j cap. Minus cx I cap and minus cy j cap. The components are just values, they are scalars. And finally, if the vector is in the fourth quadrant, let's say D, the horizontal component is dx and the vertical component is dy, then this is positive but this is negative. So you will get it as dx I cap minus dy j cap. Components. So according to the existence of the vector, in which quadrant does it exist? So you have to split the components according to that quadrant there. Now you see our tension is in second quadrant like this. So I get the components this way. So when I split this tension into components, right? So the horizontal component is Tx like this and the vertical is Ty. This is horizontal component, that is vertical component here, right? But you know the angle is with the vertical, angle is made with the vertical. So this is the adjacent component to the angle, the component adjacent to the angle. I was telling you, whenever the vector, the angle, when the angle is adjacent to it, then this will be the cos component. So therefore, adjacent, this component is adjacent to the angle. So this is the cos component. You get t cos theta it is. And this is the perpendicular component. You get it as t sin theta. So this is t cos theta and this is t sin theta. So whenever you split this tension t into components like this, then horizontal is t sin theta, vertical is t cos theta. So please don't get confused that horizontal is cos, vertical is sin. It is not like that. It is not, horizontal is not cos, horizontal is not sin there. Vertical is in sin. The angle component along with the angle, adjacent component is cos component. The perpendicular component will be sin component. And the component along with the angle. Suppose if I take another example, let me give you another example. In the same case, let's suppose this is a string. I am lifting the string. I have to find out the component of its weight mg. The weight of the body is acting in the vertical downward direction. Now I want its components along this and this direction. This is the horizontal, let's suppose, and this is the vertical. I want along these two rectangular components. This is the plane, the rectangular component along this. And given this is the angle theta, this was the body initially, right? Then about at this point, the weight is acting. This is the body on which the weight is acting. Then this is the angle. You see this is vertical line, this is also vertical line. If this angle is theta, even this is also theta, corresponding angle. Right? Now the vector. So our horizontal component, horizontal is this, our vertical is this. You know, I can split the vector into any component. It can be xy like this or this way, in this direction. I can split the vector in any two rectangular components. That is the reason why I was telling you, how many components does a vector possess? Infinite. I can split a vector into infinite components there. So therefore, now I want to split the vector into these two directions. Now come on. So this is theta, angle is adjacent to this. So I said the component which is adjacent to the angle, it's called adjacent component. Then this comes up to be mg cos. And the component perpendicular to it, now this will be the perpendicular component and this will be mg sin theta. This is mg sin theta. So this way you have to split the vector into component. Suppose a simple question like this. Imagine this is the horizontal, right? An aeroplane is about to take off like this. An aeroplane is now about to take off, actually with the velocity v, making an angle something like 37 degrees or some alpha angle with the horizontal. The aeroplane is taking off up at an angle theta there. Then what is the velocity of its shadow due to the sun just exactly above it? Sun is exactly on the top there. For example, the velocity of the shadow of this aeroplane. An aeroplane is ready to take off like this. It is about to fly at an angle alpha. Actual velocity of the aeroplane is given as v. Then if the sun is exactly above it, then what is the velocity of the shadow of this aeroplane in the horizontal direction? So actually the aeroplane is going in this direction. I want its shadow in the horizontal direction. The angle is theta. So indirectly he is asking to find the horizontal component there. So what is Vx? And this is adjacent to this component, is adjacent to the angle. So it is adjacent component. So this you can write as V cos alpha. Even you can even determine, an aeroplane is flying like this. An aeroplane is flying, aeroplane takes off like this, it's flying with this velocity. We don't know the actual velocity of the aeroplane, let us say V0, but we can measure the velocity of the aeroplane on the shadow on the ground. By measuring the velocity of the aeroplane on the shadow, you can estimate the velocity of the aeroplane. Suppose if the horizontal, the velocity of the shadow is given as Vx, then he'll ask you what is the actual velocity of the aeroplane. The actual velocity of the aeroplane is V0 and the angle is alpha. Then its shadow on the horizontal direction, it is adjacent component, it is V0 cos alpha. So V0 is Vx by cos alpha. So by knowing the component, you can even measure the actual velocity also, velocity of the thing. So components of a vector is useful to measure the values, whether you, from the vector you can find the components. If you know the components, you can find out the vector. Okay, so this way a vector can be split into components, and you can make use of such things in splitting the vectors and making some derivations or calculations like this. Okay, so in today's session we have dealt with the vector, the multiplication of vector with a multiplication of scalar with a vector, multiplication of a real number with a vector, and the splitting of the vector, resolution of the vectors, right? So you better have a glance over all these things, right? Please study on that. Recall the things what I have explained the things again and again, so that you will have an idea. In the next class, we will talk about addition of vectors, right? Thank you.